Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. The question of whether life exists beyond Earth is one of the most profound and tantalizing mysteries humanity has ever faced. For centuries, the night sky has stirred our imaginations, from the earliest philosophers who pondered the possibility of other worlds, to modern scientists who probe the cosmos with telescopes and robotic explorers. Understanding where life might exist outside our planet is not merely an exercise in speculation. It is a rigorous scientific pursuit that blends astronomy, biology, chemistry, and planetary science. Life as we know it requires certain fundamental conditions: a source of energy, a solvent in which chemical reactions can occur, and the presence of essential elements such as carbon, hydrogen, oxygen, and nitrogen. On Earth, these ingredients are abundant, combined with a stable environment that allows complex molecules to form, replicate, and evolve over billions of years. When we search for life beyond Earth, we are often guided by the principle of follow the water, because water is an incredibly versatile solvent capable of supporting a wide range of biochemical processes. Yet, the story is far richer than just liquid water, as life could arise in unexpected forms, in conditions that challenge our imagination and expand our understanding of biology. Our closest neighbor, Mars, has long captured the attention of scientists and the public alike as a prime candidate for past or present life. Evidence from orbiters, landers, and rovers reveals that ancient Mars was not the cold, arid desert it appears today. Billions of years ago, the red planet had flowing rivers, lakes, and possibly even oceans. Clay minerals and sedimentary rock layers indicate long-lasting bodies of water where chemical reactions could have fostered the emergence of life. Methane plumes detected in the Martian atmosphere suggest ongoing processes that might be biological or geological in origin. Robotic missions such as the Curiosity and Perseverance rovers search for fossilized microbes and organic compounds in the Martian soil, analyzing rock samples for signs of habitability. The tantalizing discovery of recurring slope lineae, streaks that appear seasonally on crater walls, hints at the presence of briny liquid water beneath the surface. While we have not yet found definitive proof of life on Mars, its past environment closely mirrors conditions that supported life on early Earth, making it a compelling laboratory for understanding how life might arise elsewhere. Beyond Mars, the outer solar system offers worlds that challenge conventional ideas of habitability. Moons orbiting the giant planets, particularly Jupiter and Saturn, harbor subsurface oceans beneath layers of ice. Europa, one of Jupiter's largest moons, is cloaked in a fractured ice shell with a hidden ocean kept liquid by tidal forces generated by its interaction with Jupiter's immense gravity. This ocean may be in contact with a rocky seafloor, creating the potential for hydrothermal vents, similar to those found in Earth's deep oceans, which teem with life despite the absence of sunlight. Saturn's moon Enceladus presents a similar case, with geysers of water vapor and ice particles erupting from fractures near its south pole. Analysis of these plumes reveals organic molecules and hints at the presence of energy sources capable of sustaining life. Titan, another of Saturn's moons, is unique for its thick, nitrogen-rich atmosphere and liquid hydrocarbon lakes on the surface. While Titan's lakes are composed of methane and ethane rather than water, they could offer a solvent medium in which exotic life forms might exist, challenging our Earth-centric notions of biochemistry. These icy moons illustrate that life may not be confined to the narrow, habitable zone around a star where liquid water exists on a planet's surface. It may thrive in hidden oceans beneath icy shells, sustained by chemical energy from the planet's interior rather than sunlight. Exoplanets, planets orbiting stars beyond our solar system, have expanded the possibilities of where life might exist on a cosmic scale. Advances in telescopes and detection methods have revealed thousands of exoplanets with a dizzying variety of sizes, compositions, and orbital arrangements. Some reside in the so-called Goldilocks zone, where temperatures allow liquid water to persist on the surface, The discovery of Earth-sized planets in these zones raises the thrilling prospect that habitable worlds are common throughout the galaxy. Atmospheres of these distant worlds may contain chemical signatures, such as oxygen or methane, which could indicate the presence of biological processes. Future telescopes, both ground-based and spaceborne, aim to characterize exoplanet atmospheres with increasing precision, searching for these biosignatures. Unlike the moons of our own solar system, exoplanets offer a glimpse into the diversity of planetary environments, revealing worlds with extreme climates, thick clouds, or tidal locking, where one side always faces the star. Each discovery challenges us to broaden our understanding of the conditions under which life might emerge, survive, and evolve. The concept of panspermia further expands the horizons of life beyond Earth. This hypothesis suggests that life could travel across interstellar distances on comets, asteroids, or dust particles, seeding habitable environments when conditions are favorable. Meteorites found on Earth provide evidence that complex organic molecules can survive the harsh conditions of space. If life can endure such journeys, the distribution of living organisms might not be limited to individual planets, but could extend across star systems, increasing the probability of discovering extraterrestrial life. Such a framework encourages us to consider a cosmic web of life, where planets and moons are connected through the transfer of biological material, and life is not an isolated phenomenon, but a potentially widespread feature of the universe. Closer to home, the search for life also encompasses the study of extremophiles, organisms on Earth that thrive in environments previously thought uninhabitable. Microbes living in acidic hot springs, deep ocean vents, the frozen tundra, and radioactive environments demonstrate that life is remarkably adaptable. These discoveries inform astrobiology by illustrating the range of conditions under which life can exist. If terrestrial life can flourish in such extremes, then seemingly hostile environments elsewhere, like the sub-zero oceans of Europa or the high radiation surface of Mars, may also be capable of supporting microbial ecosystems. Studying these extremophiles provides crucial insights into the potential biochemistry of extraterrestrial organisms and guides the design of instruments capable of detecting life beyond Earth. The role of technology in the search for life cannot be overstated. Spacecraft, telescopes, and landers act as our eyes, ears, and laboratories in distant realms. Robotic explorers can drill beneath icy surfaces, analyze chemical compositions, and relay data across millions of kilometers. Spectroscopic techniques allow us to infer the presence of water, organic compounds, and gases in exoplanet atmospheres. Upcoming missions, such as the James Webb Space Telescope and planned planetary probes, promise to enhance our sensitivity to subtle biosignatures and provide unprecedented detail about alien worlds. These instruments are the culmination of decades of scientific innovation, representing humanity's commitment to answering one of the most profound questions: are we alone in the universe? In addition to searching for chemical indicators of life, scientists also contemplate the possibility of detecting technological civilizations. The field of SETI, the search for extraterrestrial intelligence, explores signals in radio waves, optical light, and other forms of electromagnetic radiation that might indicate the presence of advanced life forms. Although no confirmed extraterrestrial signals have been detected to date, the mere act of listening transforms our understanding of the cosmos, emphasizing the vastness of space and the potential for life beyond the confines of our solar system. The search for intelligence forces us to consider life not merely as microscopic organisms, but as complex systems capable of communication, innovation, and technological development. It expands the scope of astrobiology into the realm of sociology and engineering on a cosmic scale. Understanding where to search for life also involves careful consideration of planetary formation, geology, and atmospheric evolution. Planets and moons are dynamic entities shaped by internal heat, tectonic activity, and interactions with their parent stars. Conditions favorable to life may arise only for limited windows of time, as atmospheres are stripped away, climates shift, or oceans freeze or evaporate. Identifying worlds in the right stage of habitability requires not only observing their current states, but also modeling their histories and futures. Ancient oceans on Mars, icy moons with subsurface water, and exoplanets in stable orbits all represent snapshots in the complex timeline of planetary evolution, where life may have emerged, persisted, or disappeared. The temporal dimension adds a layer of complexity to our search, reminding us that finding life may depend on catching it at the right cosmic moment. Beyond tangible targets, theoretical studies provide imaginative insights into possible forms of life. Could organisms exist in atmospheres of gas giants like Jupiter or Saturn, floating in layers of ammonia clouds? Could life thrive in solvents other than water, such as liquid methane, ethane, or even supercritical carbon dioxide? Scientists explore these possibilities through computer simulations, laboratory experiments, and chemical modeling, expanding the boundaries of what we consider habitable. Such work is crucial because it prevents the limitations of Earth-centric thinking from constraining our search. Life may manifest in forms that are fundamentally alien, yet still operate according to the universal principles of chemistry and energy transformation. Embracing these possibilities encourages creative approaches to detecting life, ensuring we do not overlook xenon simply because they do not conform to familiar patterns. The search for life beyond Earth is not solely a scientific endeavor. It is a philosophical and cultural journey. Discovering even microbial life elsewhere would have profound implications for our understanding of biology, evolution, and our place in the cosmos. It would suggest that life is a common outcome of planetary processes, not a singular accident confined to Earth. Finding intelligent life, though far more speculative, would challenge our assumptions about civilization, ethics, and communication across vast interstellar distances. Humanity has long gazed at the stars with wonder, and the scientific pursuit of extraterrestrial life transforms that wonder into concrete inquiry, blending curiosity with rigor, imagination with evidence. Education, collaboration, and international cooperation are vital components of this search. Space agencies, research institutions, and amateur astronomers contribute to a global network of observation and exploration. Data from missions is shared, debated, and reanalyzed, reflecting the collective effort to understand our universe. Citizen science initiatives allow enthusiasts to participate in identifying exoplanets, tracking meteor showers, and monitoring cosmic phenomena, democratizing the search for life and fostering a sense of shared purpose. The endeavor to find life beyond Earth transcends national borders and political agendas, uniting humanity in a quest that is at once scientific, philosophical, and deeply human. As technology advances, the prospects of sending humans to other worlds add another dimension to the search. Manned missions to Mars or the establishment of bases on the Moon provide opportunities to conduct in situ experiments, test life detection instruments, and prepare for more ambitious explorations of distant moons and planets. Human presence allows flexibility, creativity, and adaptability in ways that robotic missions cannot fully replicate. However, it also raises ethical considerations regarding planetary protection, contamination, and the impact of human activity on potential extraterrestrial ecosystems. Ensuring that we explore responsibly is a central principle, preserving the integrity of alien environments while maximizing the scientific return of our explorations. In contemplating where to search for life, we are ultimately asking questions about ourselves. What is the nature of life? How did it originate? And what does it mean to exist in a vast, potentially life-filled universe? The pursuit drives innovation, fosters international collaboration, and inspires generations to look up and imagine what might be out there. Every mission, telescope, and experiment adds a piece to the puzzle, bringing us closer to answers that have eluded humanity for millennia. Whether life exists as simple microbes beneath the ice of Europa, as complex organisms in the clouds of Titan, or as advanced civilizations in distant star systems, the search itself enriches our understanding of nature, technology, and our place in the cosmos. The journey to uncover life beyond Earth is ongoing, ambitious, and exhilarating. Mars, Europa, Enceladus, Titan, and countless exoplanets provide tantalizing possibilities, each world offering unique challenges and clues. Life may be widespread, rare, or exist in forms we have yet to imagine. As we develop new instruments, probe hidden oceans, and analyze distant atmospheres, our understanding of habitability expands, illuminating not only where we might find life, but also the fundamental principles that make life possible. The search transcends disciplines, cultures, and generations, inviting humanity to engage in a collective endeavor of discovery. Whether we encounter microbes beneath icy crusts, detect atmospheric biosignatures across light years, or listen for faint signals from advanced civilizations, the quest shapes our future, our science, and our imagination. It reminds us that the universe is vast, mysterious, and full of potential, and that the question of life beyond Earth is not just scientific, it is profoundly human. Mars, often called the Red Planet, continues to fascinate scientists with its enigmatic landscapes and tantalizing clues of past habitability. Beyond the evidence of ancient rivers, lakes, and deltas, Mars also presents intriguing mineralogical signatures that speak to the planet's watery history. Sulfates, phyllosilicates, and iron oxides indicate that liquid water was once abundant enough to alter rocks and create chemical environments conducive to life. Seasonal changes observed from orbit reveal recurring phenomena, such as the appearance of dark streaks along slopes, which some scientists believe may be briny water flows. The search for life on Mars is not limited to surface exploration. It extends deep underground, where microbial life could exist shielded from harsh radiation and extreme temperatures. Drilling into Martian soil and ice to retrieve samples is a primary objective of current and future missions, with the hope that return samples may reveal fossilized microbial structures, organic compounds, or even living microorganisms. Understanding Mars's potential for life informs our knowledge of planetary habitability and provides a blueprint for searching other worlds with similar histories. Venturing farther from the Sun, Jupiter's moon Europa presents a compelling environment for life that challenges our terrestrial assumptions. Beneath its thick, icy crust lies a vast subsurface ocean that may contain more water than all of Earth's oceans combined. The ice above is riddled with fractures, ridges, and chaotic terrain, suggesting dynamic processes that transport material between the surface and the ocean below. Tidal forces exerted by Jupiter's immense gravity produce internal heating, which prevents the ocean from freezing solid and may drive hydrothermal activity on the seafloor. On Earth, hydrothermal vents teem with life, hosting organisms that thrive entirely without sunlight, relying instead on chemical energy derived from the planet's interior. If similar conditions exist on Europa, it could harbor microbial ecosystems or even more complex life forms adapted to life beneath the ice. Upcoming missions, such as the Europa Clipper, aim to map the moon's ice shell, analyze the composition of surface materials, and detect signs of active plumes ejecting ocean water into space. These observations may provide indirect evidence of habitability and guide future efforts to explore Europa's hidden ocean directly. Saturn's icy moon, Enceladus, offers another extraordinary example of a potentially habitable environment in our solar system. The discovery of spectacular geysers erupting from the moon's south polar region revealed the presence of subsurface liquid water and complex organic molecules. The plumes contain salts and simple hydrocarbons, indicating interactions between water and rock beneath the ice, similar to the conditions thought to support life in Earth's deep oceans. Energy from tidal flexing provides a continuous source of heat, maintaining a stable environment that could sustain microbial life over geological timescales. The Cassini spacecraft's flybys through Enceladus's plumes collected data that suggests the ocean is alkaline, a condition favorable for life similar to alkaline hydrothermal vents on Earth. Enceladus demonstrates that life need not be confined to the surface or require sunlight. Energy from planetary interiors can create habitable niches in hidden realms across the cosmos. Titan, Saturn's largest moon, stands out as an exotic world with an atmosphere and surface chemistry vastly different from Earth's. It possesses rivers, lakes, and seas, not of water but of liquid methane and ethane. Its thick nitrogen-rich atmosphere hosts complex organic chemistry, driven by sunlight and Saturn's magnetic interactions. While the extreme cold precludes liquid water on the surface, Titan's hydrocarbon lakes may offer an alternative medium for life, operating with biochemistry unfamiliar to terrestrial organisms. The possibility of life in such a solvent challenges our understanding of biology and forces scientists to consider forms of metabolism and reproduction that do not rely on water. Laboratory experiments simulating Titan's conditions suggest that complex organic molecules could form spontaneously, creating the raw ingredients for life. Titan's unique environment illustrates that habitable conditions might exist in forms radically different from Earth, expanding the horizons of our search. Exoplanets, planets orbiting stars beyond our solar system, offer a nearly infinite laboratory to explore the diversity of potentially habitable worlds. Since the first confirmed detection in the 1990s, astronomers have discovered thousands of exoplanets, revealing planets of all sizes, compositions, and orbital arrangements. Some reside in the habitable zone of their star, where surface temperatures could allow liquid water to exist. Observations of their atmospheres through transit spectroscopy enable scientists to detect gases such as oxygen, methane, carbon dioxide, and water vapor, potential biosignatures that could indicate biological activity. The diversity of exoplanet systems challenges our assumptions, revealing worlds with eccentric orbits, multiple suns, and extreme climates. Some planets are tidally locked, with one side permanently facing their star and the other in perpetual darkness, raising questions about how life could adapt to such conditions. By studying exoplanets, we expand the scope of astrobiology beyond our solar system and consider the vast possibilities for life throughout the galaxy. The study of extremophiles on Earth provides critical insight into where life might exist beyond our planet. Organisms thriving in boiling hot springs, acidic rivers, frozen glaciers, or deep within Earth's crust demonstrate remarkable adaptability. These extremophiles show that life can endure conditions previously thought inhospitable, from intense radiation to high pressures and extreme temperatures. By understanding the metabolic pathways, survival strategies, and biochemical adaptations of extremophiles, scientists can develop hypotheses about potential life forms in alien environments. For instance, microbes living under Antarctic ice or in deep ocean hydrothermal vents may be analogs for life in subsurface oceans of icy moons, while acid-tolerant organisms could provide clues for survival in Martian soil. The study of extremophiles underscores the principle that life is tenacious and adaptable, often thriving in unexpected niches that expand the boundaries of habitability. Another crucial consideration in the search for life is the temporal dimension of planetary habitability. Planets and moons undergo dynamic changes over time, from shifts in climate to alterations in atmospheric composition and geological activity. Conditions conducive to life may be transient, existing only during specific periods of a planet's history. Mars, for example, may have been habitable billions of years ago, but today's cold, dry surface presents significant challenges for life. Conversely, moons like Europa or Enceladus may maintain stable habitable environments over extended timescales, providing enduring opportunities for life to develop. Understanding the timing and duration of habitable conditions is vital for guiding exploration efforts, determining where to search, and assessing the likelihood of discovering life. Temporal factors remind us that the search for life is not only spatial, but also historical, requiring insights into planetary evolution and environmental stability. Astrobiology also explores theoretical forms of life that challenge our Earth-centric assumptions. Could life exist in environments dominated by ammonia, methane, or supercritical carbon dioxide? Could organisms float in the atmospheres of gas giants or survive in the intense radiation of stellar flares? By modeling alternative chemistries, energy sources, and environmental adaptations, scientists broaden the possibilities for extraterrestrial life. Laboratory simulations of extreme environments help test these ideas, revealing how complex organic molecules might assemble and react under conditions far removed from those on Earth. Such research encourages creativity in the search for life, ensuring that we do not overlook forms of life that do not conform to terrestrial norms. It also underscores the importance of designing versatile instruments capable of detecting a wide array of potential biosignatures. The field of planetary protection emphasizes the ethical responsibility inherent in the search for life. When sending spacecraft to potentially habitable worlds, scientists must prevent the contamination of extraterrestrial environments with Earth microbes. Sterilization protocols, careful planning, and strict mission guidelines ensure that we do not inadvertently compromise the very ecosystems we aim to study. This responsibility extends to potential future human exploration, where the risk of introducing terrestrial life increases significantly. Protecting alien environments is not only an ethical imperative, but also a scientific necessity, preserving the integrity of life detection experiments and ensuring that any discoveries of extraterrestrial life are genuine. The quest for life beyond Earth intersects with the search for intelligence, a field explored by SETI, the search for extraterrestrial intelligence. By listening for signals across the electromagnetic spectrum, radio waves, optical pulses, or other forms of communication, scientists hope to detect signs of advanced civilizations. While no definitive signals have been found, the search informs our understanding of cosmic silence, the rarity of intelligent life, and the technological requirements for interstellar communication. Detecting intelligent life would transform our perspective, raising questions about civilization, communication, and the potential for interstellar cooperation. Even in the absence of contact, the search challenges us to think about life on a universal scale, considering the diversity of evolutionary pathways and technological capabilities that may exist across the galaxy. Technology remains the linchpin of our quest. Robotic explorers drill, sample, and analyze, providing unprecedented access to distant worlds. Space telescopes observe atmospheres, measure temperatures, and detect chemical compositions across light years. Advancements in spectroscopy, imaging, and in-situ analysis push the boundaries of detection, enabling scientists to identify subtle signs of habitability and biosignatures. Artificial intelligence and machine learning enhance the ability to process vast amounts of data, identify patterns, and prioritize targets for exploration. Together, these tools expand our reach, allowing humanity to probe environments as once thought inaccessible and to approach the question of life beyond Earth with scientific rigor. Human exploration adds an invaluable dimension to this search. Astronauts can conduct experiments in real time, adapt to unexpected conditions, and make nuanced observations that robots may miss. Manned missions to Mars, for example, could test life detection protocols, collect samples from diverse geological contexts, and provide rapid analysis that informs subsequent missions. The Moon, as a nearby laboratory, offers opportunities to test technologies, study planetary geology, and understand how humans might operate on other worlds. Human presence, combined with robotic assistance, maximizes the potential for discovery while ensuring flexibility and creativity in the search for life. The philosophical implications of finding life beyond Earth are profound. Discovering microbial life would suggest that life emerges naturally under suitable conditions, implying that the cosmos may be teeming with living organisms. Detecting intelligent life would transform our understanding of civilization, evolution, and our place in the universe. Such discoveries would impact religion, philosophy, and culture, reshaping humanity's narrative and fostering a sense of cosmic interconnectedness. The search for life is not merely a scientific endeavor. It is a reflection of humanity's enduring curiosity, imagination, and desire to understand the broader context of existence. Education and international cooperation are vital in this journey. Collaborative efforts among space agencies, research institutions, and amateur astronomers facilitate data sharing, joint missions, and coordinated observation campaigns. Citizen science projects engage the public, allowing participation in exoplanet detection, asteroid monitoring, and comet tracking. Such initiatives democratize discovery, fostering global engagement and inspiring future generations of scientists, engineers, and explorers. The search for life beyond Earth is a shared human endeavor, transcending borders and uniting people in a common quest to answer one of the most fundamental questions imaginable. As our understanding of the cosmos grows, so too does our appreciation for the diversity of potentially habitable environments. From the arid plains of Mars to the hidden oceans of Europa and Enceladus, from the hydrocarbon seas of Titan to the myriad exoplanets scattered across the galaxy, the universe presents a vast and varied landscape where life may exist in forms both familiar and utterly alien. Each discovery informs the next, guiding exploration strategies, refining theoretical models, and enhancing our understanding of the conditions that foster life. The search is iterative, cumulative, and ever-expanding, reflecting the complexity and wonder of the universe itself. The chemistry underlying life beyond Earth is central to understanding where we should search. On our planet, life relies on carbon-based molecules, including proteins, nucleic acids, lipids, and carbohydrates. Carbon's unique ability to form stable, complex, and flexible bonds makes it an ideal scaffold for the molecular machinery of living organisms. Hydrogen, oxygen, nitrogen, sulfur, and phosphorus complement carbon, participating in critical chemical reactions that sustain metabolism and reproduction. When searching for life elsewhere, scientists look for these elements as building blocks, along with liquid solvents to facilitate chemical interactions. Water is the prime candidate given its prevalence in the universe and its unmatched ability to dissolve a wide range of molecules, stabilize temperature fluctuations, and support diverse chemical reactions. Yet, alternative chemistries are conceivable. Ammonia, methane, and other liquids may serve as solvents in colder environments, supporting life forms with metabolic pathways fundamentally different from those on Earth. Understanding the potential diversity of biochemistry is essential for designing instruments capable of detecting life that may not conform to terrestrial norms. Energy sources are another critical factor in the search for extraterrestrial life. On Earth, sunlight drives photosynthesis, powering most ecosystems, but life can also thrive without sunlight, relying on chemical energy. Hydrothermal vents on the ocean floor provide heat and nutrients that sustain entire ecosystems independent of solar input. Similarly, on icy moons such as Europa and Enceladus, tidal heating from gravitational interactions with their parent planets generates internal energy, keeping subsurface oceans liquid and potentially powering chemical reactions that could sustain life. Radiolysis, the splitting of water molecules by natural radiation, produces hydrogen and oxygen that can serve as chemical energy for microbes. Even in environments with extreme cold, high radiation, or limited nutrients, life may adapt by exploiting unconventional energy sources. Recognizing the diversity of potential energy pathways expands our conception of habitability and guides where to focus exploration efforts. The exploration of Mars continues to yield tantalizing clues about past and present habitability. Rovers like Perseverance and Curiosity investigate ancient lake beds and river deltas, searching for fossilized microbial life and organic compounds embedded in sedimentary rocks. Perseverance is tasked with collecting samples that may eventually be returned to Earth, allowing laboratory analysis with techniques far more sophisticated than those possible on the Martian surface. Studies of Martian meteorites that have landed on Earth reveal organic molecules and mineral structures suggestive of interactions with water. Future missions aim to drill deeper beneath the surface, targeting regions shielded from harsh radiation where subsurface microbes could survive today. Human exploration of Mars, potentially within the next few decades, would enable unprecedented flexibility in sample collection, in situ experimentation, and rapid hypothesis testing, significantly increasing the likelihood of detecting signs of life. Europa Clipper and other upcoming missions to the icy moons of the outer solar system promise to transform our understanding of these hidden oceans. Europa's ice shell may be tens of kilometers thick, but chaotic terrain and fractures suggest material exchange between the surface and ocean below. Detecting plumes of water erupting from beneath the ice, similar to those observed on Enceladus, could provide direct access to the moon's subsurface ocean without drilling through kilometers of ice. Instruments aboard the Europa Clipper will analyze the composition of surface and plume materials, searching for organic molecules, salts, and potential chemical energy sources. Enceladus remains a particularly exciting target because its plumes have already been sampled by the Cassini spacecraft. revealing a mixture of water, salts, simple organic compounds, and even complex macromolecules. Future missions may include orbiters or landers capable of directly probing the ocean beneath the ice, potentially confirming the existence of habitable conditions or even life itself. Titan's exotic hydrocarbon seas present an alternative avenue for exploration. The Dragonfly mission, set to launch in the coming decade, will send a rotorcraft to traverse Titan's surface, sampling dunes, lakes, and other geological features. By analyzing the chemical composition of methane in ethane-rich environments, scientists hope to understand whether Titan could support life that exploits hydrocarbon chemistry. While Titan's extreme cold and lack of surface water preclude life as we know it, its complex organic chemistry may provide the raw materials for alternative biochemistries. Dragonfly will also study atmospheric dynamics and energy sources that could sustain life in unexpected ways, offering a rare opportunity to explore a world fundamentally different from Earth, yet chemically rich and potentially habitable. Exoplanet research continues to push the boundaries of our search for life beyond the solar system. Observatories like the James Webb Space Telescope, JWST, and the upcoming Nancy Grace Roman Space Telescope enable precise measurements of exoplanet atmospheres, temperatures, and compositions. By observing how starlight filters through an exoplanet's atmosphere during transit, scientists can detect molecules such as water vapor, carbon dioxide, methane, and oxygen, possible indicators of biological activity. Planetary systems vary widely, with some hosting super-Earths, mini-Neptunes, or planets in eccentric orbits, challenging our understanding of habitability. The discovery of Earth-sized planets within their stars' habitable zones, especially around nearby stars, raises the exciting possibility that habitable worlds may be relatively common in the galaxy. Advanced spectroscopy and imaging techniques will allow scientists to refine their search, focusing on planets with conditions most likely to support life. Panspermia adds a speculative yet intriguing dimension to the search. If life can survive the harsh conditions of space, including extreme cold, vacuum, and radiation, it might travel between planets or even star systems, hitching rides on comets, asteroids, or dust particles. Meteorites from Mars found on Earth contain organic compounds, demonstrating that molecules essential to life can endure interplanetary journeys. If microbial life can withstand such travel, life could spread widely across the cosmos, making habitable worlds more likely to harbor organisms with a shared ancestry. Panspermia emphasizes the interconnectedness of planetary systems and suggests that life, once established, may propagate throughout the galaxy under favorable conditions. Speculative forms of life challenge our imagination and broaden the scope of astrobiology. Life may exist without water, utilizing alternative solvents, or thrive in extreme environments of temperature, pressure, or radiation. Organisms could float in dense atmospheres, survive under thick ice sheets, or metabolize exotic chemicals unheard of on Earth. Studying extremophiles informs these possibilities, showing that life can adapt to seemingly uninhabitable conditions. Laboratory experiments simulate alien environments, testing the stability and reactivity of complex organic molecules, helping us refine hypotheses about life's potential forms. By considering diverse biochemistries and metabolic strategies, scientists ensure that searches for life are not constrained by human assumptions, increasing the chances of detection. Ethical considerations are integral to this endeavor. Planetary protection protocols aim to prevent contamination of extraterrestrial environments with Earth microbes, preserving the integrity of life detection missions. This responsibility becomes even more significant with future human exploration, where the risk of contamination increases dramatically. Protecting alien ecosystems is both a moral and scientific obligation, ensuring that any discoveries of extraterrestrial life are authentic and undisturbed. Ethical guidelines guide mission planning, instrument design, and operational procedures, reflecting a commitment to responsible exploration. The philosophical impact of discovering life beyond Earth would be profound. Even microbial life elsewhere would indicate that life emerges naturally under suitable conditions, transforming our understanding of biology, evolution, and our place in the cosmos. The detection of intelligent life would redefine humanity's perception of civilization, communication, and cosmic significance. Such discoveries would influence culture, philosophy, and religion, sparking new debates about our role in a universe potentially teeming with life. The search for life extends beyond science. It reflects humanity's enduring curiosity and desire to understand our connection to the cosmos. Education and international collaboration are essential to this quest. Space agencies, research institutions, and citizen scientists contribute to a global network of observation, exploration, and discovery. Data sharing, joint missions, and collaborative research maximize the scientific return and foster a sense of shared purpose. Citizen science initiatives engage the public, enabling participation in exoplanet discovery, meteor tracking, and analysis of cosmic phenomena. By democratizing exploration, humanity collectively engages in the search for life, inspiring generations to gaze upward and imagine the possibilities that lie beyond our home planet. In considering where to search for life, we must adopt a holistic perspective. Habitable environments may exist on Mars, Europa, Enceladus, and Titan, as well as on countless exoplanets throughout the galaxy. Life may be microbial or complex, water-based or exotic, solitary or part of a broader cosmic ecosystem. Each world offers unique challenges and opportunities, from extreme temperatures to hidden oceans, from chemical complexity to energy limitations. Understanding these environments requires multidisciplinary approaches, combining astronomy, geology, chemistry, biology, and planetary science. The search is iterative and cumulative, building on decades of exploration and discovery, continually refining hypotheses and guiding future missions. The human drive to explore, to ask profound questions, and to seek understanding propels this endeavor. As technology advances, as telescopes peer farther into the cosmos, as spacecraft probe distant worlds, we move closer to answering the question that has captivated humanity for millennia. Is life unique to Earth, or is it a universal phenomenon? The search for life beyond Earth is not merely a scientific enterprise. It is a reflection of humanity's curiosity, imagination, and aspiration to understand our place in the universe. Every mission, every experiment, and every observation brings us closer to the day when we may finally know that we are not alone. Whether life exists beneath the icy crusts of moons, in the methane seas of Titan, in the thin atmosphere of Mars, or on distant exoplanets, the pursuit of this knowledge shapes our science, our philosophy, and our culture. It challenges us to expand our definition of life, to consider alternative chemistries and energy sources, and to imagine forms of existence radically different from our own. The endeavor connects generations of scientists, explorers, and dreamers, uniting humanity in a shared quest across time and space. In the vast cosmos, with billions of stars and planets, the possibility of life is not confined to imagination. It is a question that beckons exploration, demanding curiosity, rigor, and the courage to seek the unknown.